as we have discussed day one, that the current technology or current device which makes almost every electronics component or every electronic circuit uses a device called MOSFET. 99.9, maybe a little more, but at least 99.9 circuits, base circuits are MOS circuits. So question was many times came to our mind, should we really start with semiconductor theory so much and then talk PN junctions and then come to MOSFET? Why not start with the FET first? Well, the idea was that there is something word in English called pedagogy, how it started, how its history went through. The idea behind was that as you start learning physics properly for the semiconductor, then when we really come to the device, you are already aware of what's going to happen when you see the device. And that's why this is the order we have been following, but no reason you could have started with FET day one and started MOSFET the next itself. But as I say, I being old enough, 65 going to be, I learned, by the way, you probably will not be knowing, in my undergraduate there was no MOS device known to us, okay, even not in the books. Okay. We were learning something on not even transistors. Transistors we learned very late, BJTs. We were learning on vacuum tubes. Okay. Our electronics was age old, but it worked. Even then that was working. So is BJT circuits worked, and now people say MOSFET works. So fair enough. So let's look at MOSFET now a little more carefully, because as I said, this is the device which is being used extensively in all circuits. So here are two devices shown. One is called N-channel MOS or NMOS, and this channel decides by the inversion layer you get. In the case of this device, the channel is because of, inversion layer is because of electrons. Therefore it was given a name NMOS. Whereas in this case, the inversion layer is going to be of holes, therefore it was given a name PMOS or P-channel MOS. And we already done capacitors. If you forget about this source drain regions, this like metal oxide semiconductor, so which is a MOS capacitor, which by field effect, that applying a gate voltage, I can create across the surface opposite carriers and makes it inversion layer possible, is called field effect. So this field effect is essentially coming from, if I apply bias here, let's say, so there is a electric field in either of the direction depending on the polarity, so it is called vertical fields. So when I apply a voltage at the gate, I am creating a vertical field. Whereas if you see, if I apply voltage between these two terminal, drain and source, I am going to create, let's say, called this EX and this EY. So I have, if I apply voltage between source and drain, then the electric field is lateral or horizontal, and therefore it is EY. The direction I am using, as I said other day, this direction I say Y, this direction I say X, and the third direction, which I have shown you a third dimension, it is something like this. That's the Z direction, and we'll say the width of this transistor is W. So for example, let's take a duster. This side I cannot show you. So on this side is the drain, this side is the source, this white is the channel, inversion layer, and the top yellow is gate. Okay. So if I apply electric field here or voltage here, I am creating electrons here. Or if I, let's say NMOS, I apply positive VGS greater than VT, I create electrons. This is channel length. This is channel white one. This is channel length. So this is channel width. Is that clear? So it's a three-dimensional device. Essentially the transport is along say the Y direction, but controlled by X direction. And how many will be decided by the Z direction, because this is the area or the volume it's going to get to. Is that okay? So it's compared to the BJT, which we haven't done so far, but compared there, it's a unidimensional theory, is good enough in the case of BJTs. All that we do is one directional current and area, and that's a volume is okay. In this case, this is relevant. This Z direction is relevant. Is that clear? Then The carriers here are decided by these fields and the motion is directed by the field across this. And that's why this device is more interesting or slightly more interesting than the BJT. But if you see here, I also keep seeing junctions here. It's not that only MOS is the capacitor which I am seeing here, but there is, what is this? There is a PN junction, one from the source side to the substrate, the other is from the drain side to the substrate. So essentially saying this has two diodes. So we have two diodes sitting inside this substrate from source to the ground or source to the bulk and the other from drain to the bulk, and then there is a field effect capacitor which is sitting in the center. Okay. So that PN junction little bit required here because there is a junction going on. Now in the case of MOS capacitor, we said that, let's say if I apply plus VGS, right now I ground this, both of them, okay, and I say apply VGS greater than VT, then I figure out electron channel appears. If VGS is greater than VT, inversion layer appears across complete from source to drain. Is that clear? Now the catch there is, in the normal MOS capacitor, if you see, this is oxide or insulator and this is your metal plate. This is also your metal plate. Now in this case, there is a difference between this case and this case. If this is grounded, this replicates this. But let us say if I apply a plus value here, now you can see if there is an electrons here and if I apply from source to drain a voltage VDS, this is looking like me. You have a channel which is consists of electrons, N type. Then there is this N plus, source and drain, both, N plus, I am applying VDS, and this N is essentially decided by Ex, but right now number is known. For given VGS, this N is known to me. Now I figure it out that the current flowing in this is like a semiconductor bar. It's like a semiconductor bar. If sigma is the conductivity here, then I know J is equal to sigma E, the drift current will flow. If there is no gradient, then we say drift current will flow. Okay. That means the MOS current transport is essentially because of the majority carriers N, which is essentially the drift current. In the case of PN junction, we said which current dominates in the PN junction forward current? The minority carriers, the holes from P side enter N region becoming minorities, electrons from N side entering as a minority in the P region constitute the forward current. That is, the minority current dominates in the case of PN junctions. Which is the reverse current there? It's the majority current which is smaller, but it's the majority current which is smaller. Whereas in the case of MOSFET, if there is no gradient, which we'll see possibly there is no gradient, but if it is there, we'll add diffusion terms necessary. But otherwise, the major current available in the MOS transistors is drift current. So it's like drift current is statement of which law, which is right from 7th standard or maybe earlier you are learning, Ohm's law. So we are still sticking to Ohm's law. Is that clear? So whatever Professor Chatterjee was talking, 100 volt, 1000 volt, 5000 volt, Ohm's law is still valid there as well as here. Okay. Only thing is, we didn't want to call Ohm's law there. We suddenly say, oh, there is a 4 Maxwell equation. One of them represents Ampere law and Ohm's law. Statement is same, modified to suit what we need. So now we figure out this number of carriers which are going to be created is essentially function of VGS. How much is the gate voltage I apply? That will decide how many carriers inversion layer charge I can grade. Whereas the current, I call it R drain to source, if this is my drain and this is my source, is a function of VDS. and how many, what is the conductivity I get here? Is that correct? Or to say IDS is not only function of VDS but also function of VGS. So gate voltage as well as drain to source voltage both control the current. In the case of PN junction, we said only I this way or this way, nothing like this. Here is that third one is now coming into picture. So this is what we are really looking into. How does IDS, which is the drain to source current externally I see, and equivalent circuit, if equivalent transistors, if I see, I show slightly different symbol compared to this. I'll call drain, this I'll call source, this I'll call gate, and if you say some arrow plus, we'll say this is my bulk. So a MOS transistor has an equivalent of 4 terminals. How many? 4 terminals. Okay. And one can see from here the current is only drain to source. Why there is no current here? Because there is an insulator sitting here and no DC current at least can pass from gate to drain or source. Is that correct? That's the biggest point I said earlier. Since there is no current between gate and the outputs, this is your output circuit, this is your input circuit, let's say, there is no direct DC connection between the input side to the output side. Input impedance is very, very high depending on the insulator you have, and that's why it can be connected block to block without even worries. Whereas in the case of BJT, we'll see input impedance is essentially KT by QIC. Sorry, IB. So IB is the input current and that decides the input resistance. Is that clear? Whereas, and this will be of the order of, even if microamps, tens of microamps, this is 25 millivolts, so at least few kilo ohms, 1 to 5 kilo ohms, no more, not much than that. Whereas in the MOS transistor, typically you may get 10 mega ohm to a better this, maybe 100 mega ohm. So that is the major interest when I say I have a MOS transistor whose input impedance is extremely high compared to any BJT transistor I use. Is that clear? So that is one advantage in making circuits. What is the advantage I said last time? If I don't need anything in between to connect 2 blocks of BJT, as I may require a buffer in most cases, then the number of components I put in the same area of silicon will be smaller in BJT than in MOSFET. Also, the currents which I will get in a BJT will be extensively at least few orders higher than what MOSFETs probably will provide. So what is another advantage I can get? The power dissipation in MOSFET will be much smaller compared to BJT. However, this word is always goes with a pinch of salt, because we said earlier in the day 1 that power and speed are connected. Larger the power, speed will be higher. By simple thinking, C dV by dt is the current flowing in a capacitor. Is that clear? Now if capacitor has to be charged faster, larger currents are required. Is that correct? VCC 1 minus e to the power t by RC. Larger the voltage you pump or larger the current you push, faster will be the rise. Is that correct? That means larger power will always push speed higher. We are trying to see, can we have, if not same speed as BJT, but almost same speed as BJT, even in MOSFET, but the additional advantage I should get is, power is extremely low. If I achieve that, then I say I have beaten BJTs. Because this statement is always should be taken with pinch of salts, but still one can say MOS circuits are much low power consumption circuits than BJTs circuits. Also we will say their speeds, if not higher, at least are now comparable with BJTs. MOSFET speeds are, circuit speeds are as good as BJT speeds. Low power, denser means for the same silicon area I can put larger circuit now in MOSFET than BJTs. Is that clear? So all in all it seems as if MOSFET has taken over BJTs. Is that clear to you? as if, this word is as if. If you proceed further in devices some other day, 4th year, and still continue to have interest in devices, we'll show you no, it's not so very true. There are other BJT circuits which may still be superior in some case. At least, of course, power is always the counter. You give me power and then I'll push. But the same power I give to MOSFET, I won't reach there, which BJT I will reach. So there is some advantage. One sees, of course, need not be done in silicon. Some other semiconductors, indium gallium arsenide on silicon, something other heterostructures. Some other devices, yes, they may be useful, they may be better than MOSFETs, at least speed wise. But otherwise, in all sense of the word, MOS circuits are going to remain. As I say, I being 65 may not remain another few more years, which means I will say till 2050 it may not go. You will not question me by then because I may not be around to be questioned in 2050. 40 years down I may not survive. So I am safe to say. So everyone is saying it's tapering down circuit. Now no more CMOS, no more CMOS. Last 8 years we are listening. Actually in 1987 someone said that's the end of it. Now 2011 is still going strong and improving. I said 2025 100%, by 2050 90%. When we don't know ahead of it. Unless some of you actually invent something new, which is very surprising. I am surprised by this generation, your generation, you should do better than us. Every 50 years, there is a revolution in electronics. Vacuum tube, 1950 transistor, 2000 has crossed, 10 years gone, nothing has come out drastic. I mean, few changes have come, but nothing drastic. So unless you come with something very different idea, with a different something, like brain waves, things can be done just by visualization, possibly. Okay. Of course, that may be dangerous, but possible. Okay, so our aim ultimately is to see this relationship. How does this relationship works? Okay. So we like to have two characteristics of this MOS transistor. We figure out, I can draw two currents, two characteristics. One, I can plot IDS versus VGS at, I would say, VDS small but constant. This small word is very important. Look at we will not do much about this. Whatever we do here, opposite polarity goes for here. There VGS is positive, here VGS will be negative, here power supply will be positive, here power supply will be negative. Everything which is valid here, opposite polarity is valid here. Okay, so if I apply VGS and I apply VDS small, and bulk of course I always ground right now for all devices to come, then I figure out, if I make VDS 0, then there is no current from drain to source. Is that point clear to you? If I make drain source current voltage 0, no transport. So I need VDS for current to flow. Okay. Now if that is so, but I say it's very small. Then I say if I increase IDS, I see a very small current, very small current, till certain voltage, which I call threshold voltage. Now can you see why this current exists even below VT? We have said VT only inversion occurs. No, it doesn't occur at VT. What was the condition of inversion I said in capacitor? When psi S crosses EI crosses EF, inversion sets in. But what is the definition for VT I gave? 2 phi F. So from phi F to 2 phi F, the inversion layer, though number of carriers are smaller, but it exists. This region is called sub-threshold region. Is that correct? Sub-threshold. So sub-threshold currents are not zeros. They exist there. Is that clear, ma'am? That below, from psi is equal to 0, phi f to 2 phi f, we are not declaring VT. But there is, inversion has already set in there. So this is called sub-threshold current. Beyond VT now, VGS minus VT is available to you. Large electrons can be created in the inversion channel, and depending on the sigma, which is Q mu n, J is sigma E Y I would say. And what is EY value here? VDS by L. This is called channel length. And the third dimension, if you see, this is my W. Okay. This is length, this is this, and sigma is Q mu N, mobility of this. N is decided by the Ex, the voltage I apply from VGS side. This is what I am now looking into. This I have fixed, but this I am changing. So I say if I cross VGS higher than VT, we know inversion channel is number of electrons per cc will keep on increasing in inversion channel, which means sigma will keep on increasing. That means current will start increasing, and it will show you some such characteristics. So in N-channel MOSFET, below VT, ideally what should be the current? 0, because we say threshold, turn on, below that 0. But in reality, this current is not 0. That very small, it is e to the power minus some value will appear, we'll see some other day if time permitting what is subthreshold. But otherwise you say the current is small but not 0. Is that correct? So how do I define VT? The way I define is, let's say I did little bad slope, but I extend this portion on the gate voltage axis wherever it intersects, or rather if you want very clear, you also have a slope here, and wherever it intersects, that we decide. That means wherever slope changes at least an order above, we say VT exists. Order above, you understand, like this. So when at least 10 times, if the slope changes, we say we are at the threshold. Is that clear? So it's not an exact definition. You cannot say here, somewhere here, okay. This characteristics, let's say look at from this side. I am fixing this voltage, some VDS value, okay, very small, and I am changing VGS. Is that this is the characteristic I am measuring. I am fixing VDS and measuring IDS with reference to change in VGS. This is my input, this is my output. Input to output is called what? Transfer. Input to output. So this characteristics is called transfer characteristics. This is very important for us. Why it is important? Because after all, our interest is always in finding out the output with reference to change in inputs. That's what all circuit people are looking for. So this characteristics is most relevant for us because it tells us how much is the output. Current means IDS RD will be the drops across. So how much output I can get for a given change in inputs. Okay. This fact is very important for us, that how much is this, and we will be interested to know some slopes here. What is this value will be? We will come back to it again. What is this value should be? Current by voltage, what is it called? Conductance. So it's called transconductance. In all circuits, we are interested in transconductance. How much is the transconductance? Is that clear? So this, in circuit, this is the major parameter I need to know, transconductance. Output conductance, change in output current because of change in input signal. Is that correct? So this value is of immense importance for me. How much is the transconductance I get? Is that clear to you? So having said this, I now see there is another possibility can exist. I have fixed VGS, okay, I have fixed VGS, and then let's say N is fixed now, sigma is fixed, but I am changing this value. I am changing Ohm's law kind of voltage variation. So I figure out the characteristics is not so simple like I thought, and there is where the studies look for it. Simple Ohm's law क्यों नहीं हुआ? If I apply IDS and VDS characteristic, what is this characteristic we call? IDS is the output current, VDS is the, that circuit you have seen. This is your VDS. What is this? Output voltage, output current. So what is this characteristics called? Output characteristics of the transistor. So we are next characteristics of interest in circuit is output characteristics. For one value of VGS and then multiple values of VGS, fixed values of VGS, I can calculate IDS versus, if I change VGS, what value I am going to change? N. So for different VGS, I will have different characteristics. So I figure out, it's a very funny. If it is much lower than VT, VGS is less than VT, a very small current flows. Which is this current? Sub-threshold current, very small current, okay. Practically one can even assume that to be zero in calculations in many cases, okay. However, to show it, but if I exceed VGS, I find initially current goes linearly with the VGS. And after certain value the slope changes, and so much so it becomes constant or called saturated. Is that point clear? Initially it starts rising and let it start changing its slope and it becomes constant. Okay. This is, let's say, one value of VGS. If I plot different value of VGS, VGS increasing, of course in all cases VGS is greater than. So if I see a transistor characteristics, output characteristics of the transistor, I see initially current rises with VDS and then saturates. Okay. Now these points where this is going to saturate also has some meaning. Why? It's not same value. As it goes ahead, it has different points at which this starts saturating. Now why does it saturate? That's very interesting. Why current saturates? Whereas initially it does go, what is this law essentially it is following in this region? Ohm's law. Current is rising with voltage. Is that correct? Then what happened? Why Ohm's law latter did not get followed? I mean, must be some reason that initially it looked like Ohm's law was being followed and now they say no more Ohm's law, current is constant. Okay. This is what makes we to feel that this simple model which I thought is correct all the time may not be true all the time, must be something else is happening there. Is that clear to you? This is what we want to know, why it has happened like this. So two characteristics of interest for me is, one is transfer characteristics. Okay, what is this value if I calculate at any value? What is this value here? Delta IDS by delta VDS in this region. So the resistance is infinite. Output, this delta VDS by IDS is output resistance. So the output resistance becomes as if infinite. Flat characteristics. Conductance is 0 is right. Okay. This is something interesting. Whereas if I look at this value, this is finite. That means there are three regions of MOS transistor operation. One is VGS less than VT, then VGS VDS is smaller, and then when the VDS is larger. So there are three regions in which MOSFET is operating. One is cutoff region, you may say, or VGS less than VT. The second is the region when VDS is small enough, current follows voltage. So some kind of linearity is seen, and then suddenly beyond, when VDS increase further, I find saturation. So there are three modes of regions in which MOSFET operates. Is that clear from the characteristics? Three regions, one cutoff, second linear, and third saturation. Is that correct? Three regions this device is going to operate. So we must now find the characteristics which represents these three regions. What is way we will like? Do we want to have a different characteristic equation for all three? If that happens, every time I have to remember, kya, ye kaun sa hai? I want a general equation in which whenever I substitute these three conditions, I must get the characteristic which replicates this. The catch is simple in any analysis, you should all understand. You may do something theory here, you may do something theory here, but at the corner it must meet. Okay, and that is where the boundaries are fixed actually. Okay, that's how modelers do. Idhar se ek fit karte hai, idhar se aur corner ye fit hai. Okay. Okay, so let's look. One of the characteristics which I shown here was for which device was that? NMOS. So IDS, VDS characteristics, or rather first look for these characteristics. This is for NMOS, transfer characteristics for NMOS. If I do this, if I see a characteristics, what is this device? It's a PMOS device. Now there is some few more interesting words we can say. As I increase VGS, either for N channel or P channel is more minus VGS, N channel is more plus VGS, beyond VT, I get larger currents. Is that clear? I get the larger currents. This carrier, why the currents are larger? Because inversion layer receives more carriers. Is that correct? Larger the VGS, larger is the inversion layer charge. Is that clear? Since initially at 0 voltage or less than VT value, the inversion charge was very small, and as I keep increasing VGS, the inversion charge enhances. What does it do? It increases means enhances. The two devices are called enhancement mode devices. Enhancement mode devices. Both P channel and N channel. These are called enhancement mode. Initially the charge was very small. As I increase VGS, the inversion charge rises, so the current rises. And therefore we say it is enhancement mode device. This is what circuit people are looking for. Why we are interested in this circuit device? If I apply VGS 0, I don't want current here. And if I apply VGS large enough, I want most of the current flowing at the outputs. What is it equivalently saying? No current, large currents. So what does it shows? Switch. Is that correct? Switch. For logic, I am looking for 0 and 1 values. So I can create an excellent switch when VGS is much lower than VT and then VGS is much higher than VT. I'll switch on and off this transistor. On means full current, off means no current. So I can make on off of this transistor by making enhancement mode. Is that correct? Initially off, then on. Now there is two more characteristics I can create. Of course, the only difference for P channel will be what? All signs are minus. Is that correct? All signs are minus means P channel device, all signs positive means N channel device. However, both are enhancement. When the VGS exceeds VT, the current starts rising. Initially it is 0 and then starts rising. However, I have a device, maybe I'll show you what I do. I intentionally create an N layer here. No inversion. I made an N layer already present there. Okay. So what, will there be current at, by N region I can, like N plus I made one small N region also. Whose doping I know, how many carriers I have put there. So some sigma is already created at the surface. So what will happen at VGS equal to 0? Proportional to whatever I have put, current will flow. Is that correct? If I further increase VGS, more electrons due to inversion will add to this, more current will flow. But at 0 bias itself, the current is flowing. but I want to shut it off. So what should I do? So if I apply minus VGS now, so what will it start doing? It will put plus charge here, means start depleting this N. So it actually will deplete here, and then there is no current between source and drain. So where did I switch it off? By applying minus VGS value. Though it was an N-channel device, but I needed minus VGS, some value, to turn it off between current between source and drain. These transistors are called depletion transistors. अब बताइए, यदि ये डिप्लीशन ट्रांजिस्टर NMOS है, कहां से कैरेक्टरिस्टिक्स दिखाएं? कहां से दिखाएं? ये जो कैरेक्टरिस्टिक्स कहां शिफ्ट होगी? उस डायरेक्शन में. सो यू कैन से even at zero bias there is a current. Even at zero bias there is a current, because you have put N region there, no? That current is flowing there. To shut it off, deplete it off, I will require a negative VT. This is many times called VTD, depletion device, VTD, which is for N channel it is minus. For P channel, where should I draw here? VTPD you can say. It will be plus value, because let's say here, if I created a P region here, I will require plus VGS to deplete this P. Is that correct? So that the current can be switched off. So which is this device? This is PMOS depletion. So what is the threshold of PMOS depletion? Plus VTP from plus value. N channel VT depletion is minus VT. Enhancement mode N channel device VT is positive. Enhancement mode P channel devices VT is negative. So these four things must be in mind. 99 will use only enhancement mode, but there are circuits which will use depletion transistors. In the output, where should I show, how should I, let's say it looks similar, but what should I change here to make it look like depletion transistor, N channel at least? Somewhere here, VGS, it's 0, it's conducting, below that it will reduce, somewhere here it is VTP, okay, or VTN, sorry. When it goes to this value, then negative of course, then it will be switched off finally. Above that it will act like an enhancement mode. Below that it will actually deplete out and current will go to 0, and it will require minus value of threshold to turn it off. Is that correct? These are called always on transistors. Depletion mode means always on transistors. Okay. Then why do you use it? Okay. So there is some reason to use it. It's not that we don't use it, we use it very often. And why I showed you this? Because another device which is made out of PN junctions actually uses this characteristic to some extent. That is called junction FET. Why I showed you all this? Because the characteristics of JFET, as the word goes, is essentially equivalent of depletion mode MOSFETs. Is that correct? And therefore I thought I'll show you that I can create a JFET equivalent characteristics also in MOSFET by creating some kind of pre-dope channel there. Pre-dope means before I put bias, I already some N or P region I have already created there initially. Okay. So these four devices, now you got the point. These are four possible devices to show a depletion transistors. So okay, symbolization. In the case of, okay, maybe I'll show you. In the case of NMOS, enhancement mode devices, the arrow is in for the bulk. This is NMOS enhancement mode device. Then this is This line extra channel I have shown is actually called NMOS depletion. Is that clear? If I put another line there in transistor, I already created this region. So that is symbolized by putting another area there. So this is called depletion. Then the third one, PMOS, there is no real difference except that the arrow is out, source, drain and gate. But in circuit, I have another symbol of mine which many books also uses. I put a circle at the gate to make it P channels. Okay. But this is not so much in device people, it is only the circuit people, those who use both P channel and channel, putting separate P by the circles. So this is PMOS, enhancement mode, and then this is PMOS, depletion mode. So there are four symbols which specify the four different characteristics of the MOS transistor. Is that clear? There are different characteristics of IDS, PDS. IDS, BGS are different for both transistors. Therefore, they are differently actually represented in circuits as these symbols. Okay. So far, so good. Is that okay? We have yet not solved that problem. We kept saying, oh, electrons aa gaya. But what is our main aim ultimately? Is to get a relationship for this. IDS, VDS, VGS relationship if I can get, then I say I have a characteristics which represents everything what you are really looking for. Is that correct? That is something which we want to do now. Okay. So is this figures are clear to you, every one of you? The depletion transistors have prefabricated NNP regions. Prefabricated means during fabrication there is a P layer created by us. Is that correct? In enhancement mode, it's only the substrate which is kept there. Is that correct? Okay, so these interesting points we have finished. So let's do some transistors now. We'll only use N-channel device for representation. Anything which I do for N-channel with opposite polarity is valid for P channels. ये रहने देते हैं, चलो इसको. Okay, I will tell you what is the way it looks. Let's see whether I can get this relationship. I am a priori telling you, let's say it is N channel, so mu n Cox W by L VGS minus VT into VDS minus half VDS square. This width is the width of the channel. Okay, width of the channel. Okay, L is the length of the channel, W is the width of the channel. Now one interesting feature why I wrote this expression, for a given VGS and VDS value, how can I increase the current? These are fixed, VT is fixed. Size, W by L, L is normally fixed by technology but width is my choice. So a transistor has larger width means larger currents can be drawn. Larger width means there is another issue will come. What is the larger width issue will be? Area will be larger, and also if you see Cox, which was per unit area, area is also larger, so is the capacitance is also larger. So what is the advantage? Do you get advantage? If the capacitor is larger, charges slowly. So the speed is affected. One way you are pushing the current, but your speed is going down. So there is that's the whole design is, optimization, how to get best values of W by L for the minimum value of capacitance. That's what all of us are trying in last 30 or 40 years. Okay, how to do that at different technologies. Okay, so this relationship shows that, that's what I say, this is technology, this is technology, this is technology. For the circuit person, my parameters are W by L, of course, is fixed by technology actually, but ratio of this VGS and VDS are the only thing in my hand. Is that correct? VGS is normally fixed by the technology people itself. They say maximum power supply given to you for a given technology is 1.1 volt. Finished, maximum volt. तो ये भी हाथ से निकल गया. तो करंट सिर्फ यहीं से मिल सकता है विड्थ से. Okay. That's what the designers do. So what design means? That's what I other day said. Design is always on the plan. On the top surface, whatever W's I use, that's my design. Whatever I do in the cross section down, that's the technology I do. I fix L, I fix VT, I fix everything, mobility, everything by technology. So designers have tough job because they say this is the technology, but performance is wanted is this. How do I design? Okay. That's what all the tricks of the trade in circuits are. Okay. So please remember why I keep showing you all this, because you should not feel that, technology, design, device, everything are, no, they are interconnected very strongly, and something has to be thought by every one of them so that each is helped in designs. Okay. Now I can see before we go to the real analysis whether this itself is the accurate expression or not. We will see whether it is right. This is called ideal IDS VDS VGS characteristics, or also called textbook model. What does that mean? Textbook model means, because textbook gives this, so we say textbook model. But in reality, this model is not valid in reality. But to a great extent it works in circuits. Okay. So I say, okay, silicon doesn't understand physics, chemistry, maths, good, it works. Okay. Hamara problem hai, we understand all three. How can it happen? It should not happen. We unnecessarily fight ourselves. Okay. Here, the circuit says, fine, kitna chahiye current, aa raha hai na, bas jao na. That's how circuit people work. Okay. So let's see what is the way it looks. Let us say two cases of interest. We'll come back to that little later. VGS minus VT is much larger than VDS, or VDS is very small. VGS minus VT is very high compared to VDS. One possible case. Okay. In which case, half VDS square is small. आपने बोला ना VDS बहुत छोटा है, तो स्क्वायर टर्म तो छोड़ दूंगा मैं. In that case, I see IDS is mu n Cox W by L for a given value of VGS minus VT, which is exceeding very high, into VDS. Yes, एक minute. This is fixed value, one VGS value for which this was possible. How is IDS related to VDS now? Linear. Is that clear to you? Linear. Let us say the otherwise, second case. So this is my linear region. If VGS is less than VT, there is no current, so that automatically switches off. Okay. The VGS minus VT is much smaller than, or rather equal to some value which we call VD saturation. VDS is exactly equal to VGS minus VT. VDS is equal to VGS minus, that value I call VD sat. If I substitute this here, what is the expression I am going to get? Anyone quickly? Half mu n Cox W by L VGS minus VT square. VD sat is VGS minus VT, substitute here VGS minus VT square. So this becomes VGS minus VT square half. Do you see any VDS term here? No. Current is constant, saturation. आ गया? Same equation है. If VGS minus VT is much smaller, it saturates. That's what we are saying, na? If VDS is smaller, VGS minus VT dominates, current rises linearly. Anything VGS less than VT cut off, no currents. Is that equation clear? So I must now derive next time, that is tomorrow, this relationship. And if I get this, I am representing this by one single equation. Is that correct? By one single equation. So see you tomorrow again.